no, that's not what it is. That's not what I wanted. Okay. Wow. Okay, please interrupt me if I'm too loud or too quiet at any point. Okay. Okay, time is on.
Yeah, so next we have Dmitry Mineev talking about amalgams.
Okay. Thank you for the opportunity to speak here. So I'd like to begin with the justification or something like that. So this is object-oriented, so to say. We're going to work with these four guys. In category theory, people generally love when some diagrams have limits. And in Matroid theory, it is known, it is a common opinion that it's like notoriously resistant to those attempts. And while I'm not going to answer affirmatively on any of such questions, but I think it's all going to be around that. So in particular, two main objects we work with is the tropical fiber product and tropical correspondences, which are just the attempts to construct the limits of a very simple diagrams which you would like to have limits of. But more precisely, we have two theorems, and the first theorem connects two objects, and one of these objects is very well established and studied in Matroid theory, so I hope to catch you with this. While this thing, the tropical correspondence, was not studied before, but I still hope to convince you that it's promising. Now, the third guy doesn't participate in those, so why do we need it? Well, maybe we don't, but it's just it's just the kind of object which inevitably appears in both constructions. So if we have time, we'll talk about it. If we don't, then we don't. Okay, so let's start with the definition of the amalgam. It's section 11.4 in Oxley textbook. So please write this down. But informally speaking, it's just any way to glue two matroids. Formally speaking, it means that their ground sets have a common part, intersection T, and their restrictions coincide on that intersection T. And if we have any matroid such that its restriction onto the ground sets E1 and E2 is the initial matroids that we started with, then it's called an amalgam. And already from this, you can see that this definition is really loose, that anything can be an amalgam. All four can coincide. You can take an empty intersection and take the direct sum. You can take what's called compatible one-element extensions. You can take something more geometrical, like a parallel connection, where the intersection just consists of one point, and then it's going to look like this. You can take something more fancy, which is sometimes called generalized parallel connection, when the common part is a common flat of these matroids, which has the same structure. In this case, it's just 2 points. Could be more difficult than that. So it's a very general object. But there are some special amalgams, which are called free and proper. And an amalgam is called free. It's kind of a universal criteria. If we take any other amalgam, or maybe the same amalgam M prime, and any independent set X on it is going to be also independent set in M. Well, currently speaking, this is just a reformulation. If we take the identity map on the ground set of the union of the ground sets E1 and E2 from the amalgam that we want to be free to any other amalgam, then this identity map is going to be a weak map, which means exactly that the preimage of the independent set is independent. So it's just the same thing, but we're going to need this diagram later, so I'll just leave it here. And there is even a stronger notion of the proper amalgam, which is an equality on ranks, that we expect to have a certain ranks of all flats in the proper amalgam that we wanted to sum up from the ranks of the components minus the rank of intersection. And this notion is strictly stronger than the notion of the free amalgam. It's easy to show, but the other way around, it's not true. Let's consider an example. If we have guys like this with the intersection, now the common part is just set 1, 2, 3, 4, and there is a unique amalgam in particular. It's free because it's unique, but it's not going to be proper because if we just count the ranks according to that formula on the right, then it will not work. So the free amalgam is not always proper, but the proper amalgam is always free. Moreover, they are always unique if they exist. The problem is that sometimes they don't exist. The problem is that sometimes no amalgams exist. So it's complicated. So this has been extensively researched, especially in the 80s and since then. Okay, so now I'm going to turn to the tropical part of the story. And like Graham told us yesterday and Felipe told us today, we have a Bergman fan. There is going to be a slight caveat, which is a delicate moment that I'll need a fine Bergman fan, which is a nasty thing because it just adds all those like it adds this 1, 1, 1 vector to all the cones. It's not going to affect the intuition, so all the pictures that I'm going to draw are still going to be the usual Bergman fence, the projective fence without this guy, to save intuition and to save space. But technically speaking, I need to write this down because otherwise the next dozen times I write Bergman fan and some statement about it, it's not going to be true. So if it's not affine, so let's leave it here. And then we have two kind of objects which come from algebraic geometry, which are called Cartier divisor and Weil divisor. And Cartier divisor is just a conwise linear function. So like Philippe said, tropical geometry studies partial linear functions, partial linear geometry, basically. And Cartier divisor is just exactly this. And this guy can be given by integers for all flats because the cones are generated by the rays, which are determined by flats. And all the cones are simplicial, so it's just the same as defining the values of your function on all the rays. While Weil divisor is a more geometric object, it's a balanced collection of codimension 1-weighted cones. Now, weighted just means that we attach integer weights to the cones, and balanced, well, I'm not going to give a formal definition, but I'm going to give an example which everybody sees when sees this for the first time, that if we have such a fan and we have such a piecewise linear function, then we can construct an actual graph of this function, which is not going to be linear because this guy was only piecewise linear, not actually linear. And then it's not balanced, which means that if we sum up the vectors coming out from the 0, then it will not sum up to 0. So we need to add something looking down, and depending on the slope, how exactly it was not linear, it's going to define the weight of the thing that we need to add. And then we just cut it by something horizontal, and we obtain the red point. But in general, we are going to obtain something of codimension 1. So it's a very informal process, but you'll have to believe me here. OK. So since this is a little abstract, I want to provide some translation between the, and it was all done before. I'll give all the credits. So there is a matroidal viewpoint for all of this. So as we have seen already, when I have a matroid of rank R, to which we have a corresponding Bergman fan of dimension R, since it's affine and not projective, it's going to have dimension R and not R minus 1. Now we have direct sum of two matroids. It's just a direct product, Cartesian product of the Bergman fans. Now we have a modular cut, which, let me remind, is just a thing which is upwards closed. If it contains some flat, then it also contains all the flats above. And also there is this modularity condition that if we have a modular pair of flats, then it must contain the intersection of the flats that it contains. And to this modular cut, we can take a Cartier divisor of the minus characteristic function of this cut. So it's just -1 on the flats that belong to the cut and 0 on the flats that do not belong to the cut. And if we take an associated Weil divisor, like on the previous picture, then we are going to get the Bergman fan of exactly elementary quotient, which means that we first add a single element extension, which belongs exactly to those flats which belong to modular cut, which is usually denoted in the literature like that. And then we contract that element, and this is going to give us exactly a Weil divisor of matroid n. But the good news is that we can do this many, many times, and if we have arbitrary quotient and arbitrary balanced subfan, then we can take a chain of elementary quotients, which is also very well studied in matroid theory, but from the tropical point of view, it will just mean that we have a chain of Weil divisors corresponding to those characteristic functions of the cuts. And together, if we sum up all those functions, we'll have a rank decrease function, which is just like for each flat, how much lower did it go. And from this, we can restore the characteristic functions in the unique way. And we just have to take consecutive Weil divisors according to those. And there is one special case of this construction, which is very important for us, that if we take a diagonal quotient of the direct sum of matroid with itself, which means that the copies of the elements are just parallel elements, then so this is a diagonal quotient of exactly half rank, then it's in particular a special case of this construction. So there are functions which we are calling phi's, which cut out the diagonal subcycle. So this particular language should be credited to Lars Sallermann, George Francois, and Johannes Rau. But it would be a shame not to mention this idea of the tropical geometry being locally consisting of something matroidal was very popular, and so there were very many people who dealt with it and contributed to it. So in particular, we should name David Spire, Alex Fink, Chris Shaw, Alex Esterov, and even before them, many people like William Fulton, Bernd Sturmfels, Grigory Mikhalkin, maybe Michel Biron. So really a lot of people, and I was not really around at that time, so I'm sorry if I forgot to mention someone. So now we can finally define the tropical fiber product, which uses this last diagonal construction. And it looks like too much to chew in one bite, so we'll split into parts, but for now let's just read it once. So we have two projections induced by the embedding of the common part of the ground set. And we have the product of those projections, which we just denote pi. And then we take a lift of the functions phi I, which cut at the diagonal of the matroid below. And the pullback is the usual thing, that the value on each flat is calculated by sending the flat down and seeing the value of the original function on that flat. So once again, how does it work? So we have a product of the common part of the matroids with itself, and there we have a diagonal, which is cut by the functions phi I, and then we can leave them by the projections, and then we can intersect, we can take the Veil divisors of these functions above. And this is what we call the tropical fiber product, but for now it still doesn't make any sense, so let's consider some examples. So this object was defined in around 2013 by Francois and Simon Hampe. And what they observed is that this is always a subset of the set theoretical fiber product. And what does this mean? It means that the set theoretical fiber product is, as usual in set theory, just the pairs of points which are projected to the same point of B of n. And moreover, if either of the projections is what they call locally surjective, we will see this on the example what this means exactly, then an equality is obtained. And what is easier to observe, that local surjectivity of any of the projections is just equivalent to the common part of the matroids being a modular flat of any of the matroids. Okay, but it's interesting to think about what happens if neither of the projections are locally surjective. And let's consider a very simple example. We have two uniform matroids of rank 2 of size 3, and we try to glue them together, and we have these two projections. We have already seen in Felipe's talk that this is how the Bergman fan, the projective Bergman fan of each of these guys looks like. Now it gets projected to the Bergman fan of the U22, which is just two rays looking like this. And we can see that if we take the set theoretical fiber product, then it's going to have this two-dimensional column, because each pair of points in the rays 3 and 4 is projected to the same 0 point of the B of n. So it means that this is not even a pure dimensional fan. But if we get rid of the set theoretical guy and construct our guy, then it will be exactly the Bergman fan of the proper amalgam. And now we can formulate the first theorem. The first theorem is that this is not a coincidence, that this is what always happens. So the proper amalgam exists, and its Bergman fan is isomorphic to the tropical fiber product if and only if the tropical fiber product has only positive weights. We have seen that the Veil divisors can have negative weights, and having positive weights just means basically that all the functions that you used were concave in some sense, or convex if you look from below. So of course, we cannot prove this theorem, but we can at least see how it fails to happen. So we have seen the example of the free amalgam, which is not proper. And after 2 steps, we have 3 steps, because the intersection has rank 3. So we have to do 3 Veil divisors. And after we have done 2 of them, we have such a matroid, such a matroid of rank 4. And it has these 2 flats, which belong to the next modular cut. But the intersection is not going to belong to this modular cut, and therefore this cut is not going to be modular, because 5, 6 is not contained in the intersection of the sets, so the pullback of this function is just 0. So this guy does not belong to the next modular cut, and this characteristic function doesn't give us a Bergman fan. And this is exactly what happens. This is the reason for this not to be a positive tropical fiber product. Okay, so at this point, we have almost managed to reverse the diagram. So we have seen this diagram of the embeddings of the parts of the matroids in the amalgam, and to this we have a corresponding tropical fiber product which projects down to the components. And in the example that we considered, it looks like this. But we have another part that if we have any other amalgam which is not free, so our proper amalgam is free in particular, then we can take a weak map from the proper amalgam to any other amalgam, and we have just a trivial amalgam with 2 parallel elements. And the issue is that there is no way to reverse this error, because if we can see the Bergman fan of this second amalgam, then it's going to look like this, and it's easy to see that in order to agree with both projections, you just need to be an embedding, and the embedding doesn't work because the support of Bergman fan of this upper amalgam is not contained in the support of the Bergman fan of the proper amalgam. And at this point, it looks like something we really shouldn't do, but we will anyway. So we consider the product of this Bergman fence, and since I'm kind of out of dimensions here, I'll have to draw it in something like this. So at each cone of B of m, including the 0 cone, I have the copy of B of m prime, and then I take a subcycle there, which has blue rays as positive rays and red ray, a single red ray as a negative ray. And now, what does it mean for this guy to be okay? What does it mean for it to agree with the projections? Well, you'll have to believe me for now that it means that we have to project it to B of m1 times B of m prime via the projection of B of m to B of m1. And then it has to be just an actual graph of the trivial map from m prime, because m prime is isomorphic to each of the starting matroids. And this is exactly what happens, because if we project horizontally, for example, then the red guy is going to be eliminated with the blue guy, because they're going to project to the same 0 point, and the red and the blue guy will be eliminated. And of course, symmetrically for B of m2. So this is what we want to generalize. And so it works like this. First, we make a trivial definition that the tropical correspondence is just any balanced subfan in the product of Bergman fans. And they form a category. And this is just a verbatim copy from any algebraic geometry intersection theory textbook. So the identity is the diagonal fan that we've already seen. And the composition is kind of tricky to define. So if we have two subcycles, what should be considered the composition of these guys? Well, we need to leave them to the product of all three objects. Then we need to take the intersection of the pre-images, where the intersection is just what Graham told us yesterday. It's the intersection, the tropical intersection, the intersection in the chow rings of the probotahedron variety. So it's just the same thing. It has many names. And then we have to project it to the first and the third component. So it looks like a little tricky, and the composition is associative for some reason, though it's really difficult to verify. I mean, it's not difficult, but it looks difficult. The issue is that if we take all tropical correspondences, there are going to be too many of them. It's not a very interesting object to study. And if we take only the actual graphs, we have already seen that there are too few, so we're not going to be satisfied with them. So what we do is that we define a weak lattice map, which is a natural generalization of the weak map. It's a map of lattices of flats of two matroids, which has this weakness condition that the rank doesn't grow, and also it needs to be non-trivial in the sense that it doesn't. We don't want to send the non-trivial flat into the empty set. And additionally, we say that this guy is covering if the covering relation in the pre-image implies the covering relation or the coincidence in the image. And so now, please stay with me. This is a function which looks scary, but we have already seen it. This is a function attributed to the weak map. When this is just an identity, we have the rank decrease function of the diagonal quotient, and we've already seen what this is. So the first summon should be thought as the final rank. Like, of course, it's not going to be an actual rank of the matroid, but after what we have seen, we don't care so much. And the minus things are the initial rank. So it's like, in some sense, a rank decrease function, though it's not an actual rank satisfying the rank axioms. And as before, once we have such thing, we can decompose it into the characteristic functions of the things which we call the cuts. But if we want them to actually be the cuts, the initial map must be covering. So it means that these are just the minus characteristic functions. They sum up to the function gamma, and that they're growing, that each next is larger than, covers the larger part of our flat lattice than before. And then, like before, we take consecutive Weil divisors of those functions. And finally, we can formulate the second theorem, is that if these weak lattice maps are covering, then this construction is functorial, that the actual composition of weak lattice maps coincides with the awful composition of correspondences in the geometric sense. So I think I'm almost out of time. So there is another section which I'm not going to explain because I don't want to be ashamed in front of enlightened audience. So this is just a posset. This is in both these theorems, we have to work with the things which are not Bergman fans. So what are they? So these things are the natural generalizations of Bergman fans, which are like the posets which still have the submodularity condition. They are ranked posets with submodularity conditions, but they're not actual. They're not actual geometric lattices, because they might have something like non-unique join like they might not have a joint because the set of things covering two flats may not have a minimal element. But in any sense, it's like a simple relaxation of the conditions that we have for the posets of the Bergman fan, for the posets of lattice of flats, and the things that arise in both constructions in tropical fiber product in graph correspondences is they're both the what we call a flag fan, but this needs to be axiomatized better because I have just dealt with this as it appears naturally, because when we do a cut function of the flag fan, it stays a flag fan. So I was only interested in the inductive approach, while this thing can be axiomatized, and this is one of the things I would like to do, or I would like someone else to do. So I'd be happy to answer the questions if we have time, but not these because I don't know how to answer them. Thank you. I'll stop here.
Thank you very much. We do have time for questions. Does anyone have any questions?
Can you use any of these insights to construct other examples of tropical ideals, or excuse me, of Bergman fans which are not realizable as spectra of tropical ideals, something like that?
We'll have to brainstorm this, I think.
Okay.
Okay, if there are no more questions, we'll have a break until 10:55.